In a previous lesson, we discussed how to come up with a Pythagorean identity that is generated from taking the Pythagorean theorem a squared plus b squared equals c squared, equating that to a unit circle triangle where a and b are x and y, and c, the hypotenuse, is 1. Replacing x with cosine squared and replacing y with sine squared led us to the first Pythagorean identity listed in the top corner of this table. Sine squared plus cosine squared equals 1. You can also consider other forms of this Pythagorean identity by moving one term from the left side of the equation to the right. For example, if you subtract cosine squared from both sides of the equation, you will come up with sine squared equals 1 minus cosine squared. Or if you subtract sine squared from both the left and the right of the first equation, you will get cosine squared equals 1 minus sine squared. All three of these forms are equivalent. They are all the same exact equation, but they do demonstrate different concepts of this Pythagorean identity, namely that it is malleable, that you can use it in many different forms. You will not always see situations where we have a sine squared plus cosine squared in an expression and we can replace that with 1. Sometimes you might see 1 minus cosine squared, and you can replace that with sine squared. Or there are going to be other applications of this that we will see in a moment. But first, what we're going to talk about are what are considered other Pythagorean identities that relate the other trig functions with each other. In order to generate those, what we will do is take the first Pythagorean identity, sine squared plus cosine squared equals 1, and we are going to divide both sides of that equation by one of the trig functions in that equation. For example, if I take sine squared plus cosine squared equals 1, and I divide both sides, say, by cosine squared, that will divide every term in this equation by cosine squared. That means that the second term on the left side will simply become a 1, but the other two terms we now can change based on the identities established in the previous lesson. Sine squared over cosine squared would be the same as sine divided by cosine taken to the quantity or the exponent of 2. Since we know sine over cosine is tangent, that means sine squared over cosine squared is tangent squared. 1 over cosine squared would be the same as 1 over cosine quantity taken to the second power, meaning that we can also write the fraction on the right side of this equation as secant squared. This is going to be one of the other Pythagorean identities. And just like with the other alternate forms from sine squared plus cosine squared equals 1, we can come up with other versions of this same identity by moving one term over to the right side. If I move the 1 over to the right side, I will get tangent squared equals secant squared minus 1. Or if I instead move tangent over to the right, I will get 1 equals secant squared minus tangent squared. Again, these alternate forms are not other equations that you should memorize. However, it is good to be familiar that these equations can be maneuvered. We could do the same concept to come up with another Pythagorean identity that involves the other two trig functions that we have not worked with yet. Instead of dividing both sides of sine squared plus cosine squared equals 1 by cosine squared, I will divide instead by sine squared. If I divide both sides of this equation by sine squared instead, the first term will now become a 1. The second term, cosine squared over sine squared, will become cotangent squared. And 1 over sine squared will equal cosecant squared. That is the third of what are considered the Pythagorean identities. The other forms, yet again, you can derive by moving one term over from the left over to the right. If I move cotangent squared over to the right side, I will get 1 equals cosecant squared minus cotangent squared. But if I instead move the 1 over to the right side, I will get cotangent squared equals cosecant squared minus 1. These are the Pythagorean identities that we will use quite a bit throughout this section. One note about these Pythagorean identities and how you tend to see them. Careful note on, say, the alternative form for the first Pythagorean identity. Sine squared equals 1 minus cosine squared. If you look at what we have on the right side, 1 minus cosine squared, you can also consider that as 1 squared minus cosine squared, which means that we have what is called in algebra a difference of squares. In algebra, when you have a difference of squares, such as a squared minus b squared, that can be written as a multiplication of two factors. It can be written as multiplication of the factor a plus b times the factor a minus b. Meaning, if I see this for trigonometric functions, such as 1 or 1 squared minus cosine squared, I should be able to write this as the multiplication of the factors 1 plus cosine of theta times the factor 1 minus cosine of theta. This concept can apply to all the Pythagorean identities that involve a difference of squares, which, if you look at the alternate forms, there are many of them. We sometimes also refer to this as a Pythagorean conjugate, or Pythagorean conjugates. 1 plus cosine and 1 minus cosine. These are called conjugates because they, when multiplied, equal a difference of squares. Let's look at the strategies that we're going to use for verifying identities, such as using these concepts. Let's now move on to the strategies you may use when verifying identities. In this section, we're going to talk about some of the strategies that you can use when verifying identities. Take note that these are not the only strategies and the only ways that you can verify identities in this section, but they do outline many of the common strategies that you will see. The first strategy that is recommended is to try working on what is the most complicated side of the identity. Furthermore, it is usually recommended to stick with only one side of the identity unless you get stuck, in which case you should try to work with the other side of the identity and see if you can find a way to bridge the two parts of your work. This is a very important concept. Remember that in an identity, what you are trying to do is you are trying to demonstrate that the left side is equal to the right side. What that means is that we do not know if the equality is valid yet, meaning that you should not be trying to do anything where you multiply, for example, both sides of the equation by any value or any function. You cannot do that because that is only valid when you know that the equality is true. In these cases, we do not know that, so it is recommended to simply work on one side of the identity and use other established identities, such as the Pythagorean identities, to maneuver around the trig functions that you see. The second suggestion here is to try using reciprocal and quotient identities from the previous lesson to write functions on one side of the identity in terms of the functions on the other side of the identity and simplify. Just because you cannot move things from the left to the right side of the equation doesn't mean that you are not allowed to look at the other side of the equation. Very often, looking at the solution or the other side of the equation can help to give you an idea of where you're going. The reciprocal and quotient identities from lesson 4 can help us with that, particularly when you get very stuck. When in doubt, you can also try to use these identities to turn everything into sine and cosine functions, which can sometimes help. Not every single circumstance will you want to change everything into sine and cosine. Sometimes that actually makes the situation a little bit more complicated and harder to work with. Very often there are more obvious ways or more obvious identities to apply, but it is a good default if you do get really stuck. For the third strategy, you can also try to add rational expressions with unlike denominators by obtaining common denominators. If you've taken an algebra course, this should be pretty common knowledge, that if you want to add two fractions together, you need to get a common denominator. However, keep in mind here that the fractions you will be adding aren't necessarily going to just be 1/2 plus 1/3. You are very commonly going to see fractions that involve trigonometric functions in them. For example, a fraction of 1 divided by the quantity 1 minus cosine of theta. When you see something like that and you want to combine it with another fraction or something you can write as a fraction, the first thing you should be doing is trying to find common denominators, or ways to get a common denominator between the fractions you want to combine. As a fourth and final suggestion, we have that you can use the Pythagorean identities established earlier when you see trig functions taken to a second power or to simplify sums or differences of squares to one term. Basically, what this means is if you ever see a trig function taken to a second power, the first thing you should be thinking about is probably a Pythagorean identity. For example, if I'm working through a case where I have sine squared, I should immediately be thinking about the first Pythagorean identity, which can allow me to replace sine squared with the expression 1 minus cosine squared. In terms of fractions, you can also try to multiply the numerator and denominator of fractions by Pythagorean conjugates in order to take advantage of those Pythagorean identities. Remember, from the alternate forms that are differences of squares, remember that the alternate forms of the Pythagorean identities demonstrated earlier show that you can consider expressions like 1 minus cosine squared of theta as a difference of squares, which means 1 minus cosine squared of theta could be thought of as 1 minus cosine theta and 1 plus cosine of theta. If you happen to see fractions that involve two Pythagorean conjugates like that, you can then use its associated conjugate as a multiplication term for fractions in order to get to the Pythagorean identities. This is a very common concept and strategy that you will see demonstrated in many of the examples throughout Lesson 5.